Okay, sure. This is the final revision. Now we'll go through the content one by one. Each unit, inshallah, we will try to find the specific details and discuss them all, inshallah. Unit one, we started off with um, quantities. We started off with measuring the quantities, describe the use of rulers, how to use the rulers, okay, how to measure a variety of time intervals, how to use the stopwatch, okay. I guess we all know how to use a ruler. I guess we all know how to use a stopwatch and how to measure the time from a stopwatch. Determine the average value for a small distance and a small interval. When we use the average, remember when we used the average, if we had, for example, 1,000 sheets of paper, we will take the distance or the thickness of these 1,000 sheets of paper and then divide the thickness by 1,000. If we had the oscillations for pendulum, we would take, let's say, 10 or 20 oscillations and then divide the time by 10 or 20. So the whole point is using the average. What we are required to know is the core, okay, content only, not the supplement, okay? You're not required to know the supplement. You're not required to know anything on the right-hand side, only on the left-hand side. Okay, moving on to motion. Defining speed, speed equals distance over time. Okay, we know that. Okay, speed equals distance over time. Velocity is a new concept for us. Velocity is a new concept for us. What is velocity? It is speed in a given direction. It is what, شباب? It is speed, but in a given direction. For example, if I'm moving north, okay, if I'm moving north with a speed of 10 meters per second, so what is my velocity? My velocity is 10 meters per second due north. The direction would be north. If the direction was west, I would be moving in the west direction. If whatever direction, I would be moving in that direction. But whenever I have a direction, that would be the velocity. What's your question?
مستر لو احنا بنراجع ايه بالظبط بس عشان بس ادخل.
The whole syllabus. Okay. Okay. Again, using average speed, total distance over total time. Okay, we know that. Total speed over total time, total distance over total time. Distance time graph. Okay, distance time and speed time graph, and the difference between them. Distance time and speed time graph, and the difference between them. How can we find a distance time graph, or how can we find the speed in the distance time graph? The speed in the distance time graph was the slope. Slope was the speed in the distance time graph. What about the slope in the speed time graph? The slope was the acceleration. You weren't required to calculate the acceleration. You just need to differentiate between a car that is accelerating more or a car that is accelerating less. That's all you're required to know. You're not required to actually calculate the acceleration. You need to understand the difference between acceleration and deceleration. That's what you are required to know. Okay. And then we need to know the different shapes when it is at rest, when it's moving with a constant speed, accelerating or decelerating. And I guess we all know them. We can quickly revise. If it is at rest, this is at rest, distance time graph, distance time graph. This is at rest. This is increasing constant speed. This is constant speed. Okay. And this is an increasing speed, distance time graph. Okay. And this is the distance time graph for a decreasing speed or slowing down. Calculate the speed. Yes, how can I find the speed from a distance time graph? How can I find the speed from distance time graph? It is the slope. It is the slope, y2 minus y1 over x2 minus x1. That's it. That's what you are required to know. Then, of course, we know that the area under the graph would give me the distance and that the acceleration or the g is 9.8 meters per second. Okay, weight equals mg. We know that weight equals mg and g is 9.8 meters per second squared. Okay, Again, if you have any questions, please raise your hands. Okay. And then we discussed mass and weight. And the difference between the mass and weight. State that the mass is the amount of matter. It's the amount of matter. State that the weight is a gravitational force. Okay, it's a force. The difference between mass and weight is that the weight is a force, mass is the amount of matter. The mass usually doesn't change, but the weight could change if the gravitational attraction changed. For example, if I move from one planet to another, the weight will definitely change. Okay, I can calculate G equals W over M. Yes, because I have the triangle. Weight equals M and G. This was probably the first equation that we had in our syllabus. And then know that they can be compared using different balances. Okay. Then we discussed density. Density equals mass over volume. Again, this was the second equation we had. Okay. Density equals mass over volume. The definition of density is what? It's the mass per unit volume. Mass per unit volume. Describe how to determine the density. We know the different ways to determine the densities of objects and of liquids. Okay, how to find the density of the liquid using the measuring cylinder, how to find the density of a regularly shaped solid, length times width times height to find the volume, and then we can use the balance to find the mass. Also, of an irregularly shaped object, we would use a measuring cylinder to find the displacement. We will measure the volume one, the liquid or of the water, and then when we add the weight, when we add the solid, the liquid, the volume of the liquid will increase. So we will find the difference in the volume, and this will give me the volume of the irregularly shaped object. Okay? Determining whether an object floats, definitely. It floats if its density is less or greater than the liquid. We always talk about the density of the liquid. If the object has a density less than this liquid, it will float. If it has a density which is more than the liquid, it will sink. Okay. I guess this was a bit easy. Again, if you have any problems, please don't hesitate to ask. Then we moved on to forces. Okay, we moved on to forces, the third lesson we had in the syllabus. Know that the force may produce changes in the size and shape of an object. Definitely, yes, we know that the force can change the size, it can change the shape, and it can change the direction or the speed of an object. Sketch a plot, okay? Sketch, plot, and interpret a load extension graph, okay? We know the load extension graph. You don't understand the last part. Which last part? Please be more specific, okay? Load extension graphs. This was when we were talking about the Hooke's law, okay? The density part, you have a problem with the density. What's the problem with density? Density equals mass over volume, okay? I'm sorry, I'll go back to density. Density equals mass over volume. Okay, to find the volume. Okay, the most difficult part was finding the volume of irregularly shaped objects. If I, for example, have I have an object, I have a stone, I have this volume. It's a weirdly shaped object. I cannot find the length and width and height of this object. What do? I use a measuring cylinder. I use a measuring cylinder. Initially, the measuring cylinder has some water, so I'll measure volume one. When I put this object inside the water, what will happen? The liquid will increase, so I'll measure volume two. To find the volume, what will I do? V2 minus V1. Okay, this is to find the volume of this irregularly shaped object. Okay. Um, okay. Anyway, I hope this answers your question. Okay. Moving on or moving back to forces. Again, we were talking about Hooke's law, and we are required to know the um, load extension graph. We are required to know or to find the extension due to a certain load, or to find the load due to a certain extension, vice versa. Okay. And then we can find the resultant of two or more forces. Yes, we can find the resultant forces. How do we find the resultant force? If I have an object with two forces acting this side and then one force acting on another side, for example, this is 10 newtons, this is 30 newtons, and then this is 20 newtons. Uh, Instead of 20, we can just write down, for example, 15 newtons. Okay, so finding the resultant force, this will be 40 newtons to the right and 15 newtons to the left. 40 minus 15 would be 25 newtons, and the direction would be to the left, to the right, I'm sorry. Okay, 25 newtons to the right. And that's it. That's how we find the resultant force. Okay, a resultant force of zero. Okay, know that an object either remains at rest or continues in a straight line at constant speed unless acted upon by a resultant force. What does this mean? It means that if I have a resultant force of zero, when F equals zero, resultant force equals zero, the object is either at rest or the object is moving at a constant hmm, speed when the resultant force is zero. And I guess we all know that. Again, if you don't know it or you've forgotten it, please try to remember it. If an object is moving with a constant speed, then it has a resultant force of zero. What happens if the resultant force is greater than zero? Then the object is accelerating. Okay, let's write it down. For example, if the resultant force is greater than zero, then the object is accelerating. What do I mean by accelerating? Its speed is increasing. What if the object or the resultant force is less than zero? It has a negative resultant force. What's happening to the object? It's decelerating. Okay, deceleration means that the speed is decreasing. Okay, means that the speed is decreasing. Yes, what's your question? Hmm.
يعني مستر لو مش في كل الحالات resultant force هيكون زيرو فهيكون constant speed مش ممكن يكون stationary.
ما هو it's either stationary or it's moving at a constant speed. Okay, if it already has, let's say, a driving force, if it has a driving force, and I tell you that the resultant force is zero, that means that the driving force is equal to the resisting force, like the friction or like the air resistance. Okay, if it's moving at a constant speed. But if there is no driving force, then there is no friction or a resistance. Therefore, it would be at rest. Okay, تمام؟ ماشي. State that the resultant force may change the velocity. Again, we just said it. It could, if the resultant force was greater than zero, it would accelerate. If it's less than zero, it would decelerate or the speed would decrease. Okay. Friction, air resistance, and water resistance, they are all resistive forces. Solid friction, force between two solids. Okay, for example, while walking on the ground, there's a force of friction between you and the floor. Okay, this is called friction. Okay, it's between, let's say, two solids. Friction, we can call it drag. Okay, in liquids you can call it drag, you can call it water resistance, you can call it upthrust. There are many things you can name it in the water. Okay, and air, we name it what we named air resistance. So any motion, okay, any motion will cause some sort of resistance. Any motion in air or in liquid or above a solid, okay, will cause some sort of resistance. The only case in which no resistance occurs is if you're driving or moving through a vacuum. Let's say you're moving in outer space. That's the only case, ya shabab, in which no friction occurs. Okay? Okay, good. Next point, we talked about the moment. Moment. Moment is what? Moment is the turning effect of a force. Moment is the turning effect of a force. Describe the moment of a force as a measure of its turning effect. Okay, define what is moment. It is the turning effect of a force. About a pivot, for example. Define the moment of a force as moment equals force times the perpendicular distance. Okay, that's why I have to say perpendicular distance from the pivot or to the pivot. Okay, we have to use the equation. Okay, moment equals force times perpendicular distance. Again, the unit was usually Newton dot meters or Newton dot centimeters. The principle of moments. What's the principle of moments? Basically, when we said in equilibrium, okay? When we said in equilibrium, there was no resultant force and no resultant moment. Clockwise moment. Hmm. Clockwise moment equals the anti-clockwise moment. Okay? Okay. Center of gravity or center of mass. What is meant by the center of gravity? Again, we said it was a point at which, okay, it is a point at which the whole, okay, the whole weight, okay, the whole weight of an object, okay, acts, okay. It's as if or seems to act. Instead of saying acts, we'll say seems to act. Seems to act. It's as if all of the weight is centered at that point, and that's why it's called the center of mass or center of gravity or center of weight. Okay. We had some experiment to determine the center of mass of an irregularly shaped lamina or piece of card. What did we do? We used to hang this piece of card from different um, from a pin. For example, we had a small hole in that card, and then we hanged it from a pin. Okay, and then we drew a vertical line using a not using a ruler. We had to put the if you remember, we had to put the string, and the string was attached to a small weight below it, and then we had to draw a vertical line, and then we had to repeat the experiment to find the center of mass, because the intersection of the two lines that we would have drawn would have been the center of mass of this lamina. Okay, it is not one of the very famous questions that we have in our paper 3, but it's there. Okay, so if you don't remember it, please go back and try to solve one of those questions. Okay, you would find them in the moment questions. Okay, describe qualitatively the effect of the position of the center of gravity on the stability of objects. Again, the stability, how did we describe if an object was more stable or less stable? If the center of mass was up, as you increase the distance of the center of mass above the ground, the stability would be less. Whenever you decrease the distance between the center of mass or center of gravity and the ground, the stability would increase. How? How? For example, if I had an object like this and another object like this one, which of them is more stable? The one on the right. Why? Because the distance between the center of mass and the ground is quite short. Let's say this is only 1 centimeter. But the distance between the center of mass and the ground here is a lot it's greater. Okay, so it would be less stable. Let's say this is 3 centimeters. So as you increase the distance between the center of mass and the ground and the surface, what happens? The stability decreases. As you increase the distance, the stability decreases. Okay. Okay. Again, if you have any questions, please do not hesitate to ask. Again, you're not required to know momentum. Don't worry about it. Moving on to energy. Moving on to energy. State that the energy may be stored. We have several types of energies. We have several types of energies. Gravitational, kinetic, okay, chemical, elastic, nuclear, electrostatic, internal energy, which is thermal, okay, electrostatic, which is the electric energy. Describe how energy is transferred between stores. Okay, how can we transfer energy from gravitational potential energy to kinetic, okay, or to heat, or to all the other different types of energies, okay? Sound, okay? We have uh several types of energies. Okay, know the principle of conservation of energy. Yes, we know the principle of conservation of energy. What is the principle of conservation of energy? Energy cannot be created nor destroyed. It can only change from one form to another. Okay. Okay. This part. Simple flow diagram. What is a simple flow diagram? A simple flow diagram is basically if I have an input, okay, this input will be divided into one or more than one output. For example, if I had an input of uh, let's say electrical energy, okay, electrical energy in a lamp. For example, if I had some electrical energy input in a lamp, okay, this is a lamp. The output energies of this lamp would be the output energy. Okay, we have two outputs. We have two outputs. We have light and we have heat. But we say that the light is the useful, and we say that the heat is the wasteful. Okay, wasteful. Okay, if the input was 500 joules, then the output has to also be 500 joules. If the light was 100 joules, then the wasteful or the heat would be 400 joules. That's all you're required to know. Okay, that's all you're required to know. That's it. This is input and output. Input has to be equal to the output. Okay? Okay, good. Work. Work done equals force times distance moved. Okay? It's one type of the energy transferred. Okay, it's the work done equals in force times distance moved. Energy resources. How do we produce electrical energy? How do we get all of the electrical energy we use in our daily lives? We have several sources. Okay, we have several sources. We know the fossil fuels. One of the lesser known sources is called the biofuels. Okay, the biofuels, which are the wastes of the animals. We can use the wastes of these animals and burn them to produce electrical energy. It's almost the same. It's almost the same as the fossil fuels. You take this biofuel, you burn it, produces heat. You use this heat to boil water, and the water turns into steam. The steam rotates a turbine, and the turbine rotates a generator, and then you've produced some electrical energy. Okay. Tides, hydroelectric. Okay, we know them. Geothermal, nuclear, light from the solar cells, okay, infrared and solar cells and the wind energy. Okay. Um, Again, we have to remember that we have a turbine and a generator. Turbine and a generator. A boiler, again, is used in the fossil fuels, it's used in the biofuels, it's used in the nuclear fuel. Okay, you don't have a boiler in the geothermal. Okay, the water boils on its own due to the heat generated by the hot rocks. Okay, describe advantages and disadvantages. Okay, we remember them. If you don't remember them, please try to just quickly read through them. Okay, just quickly go through the advantages and disadvantages of each of them. Okay, each of these resources. Okay, and again, finally, when we talked about the efficiency, okay, you're not required to actually calculate the efficiency. You're not required to calculate the efficiency. What you're required to do is just have a basic understanding of what efficiency is. Again, what was efficiency? It was like a ratio. What was efficiency, شباب? It was like a ratio of the wasteful energy and the useful energy. If you waste a lot of energy, then you wouldn't be that efficient. Okay? The more energy you waste, let's say if when the energy wasted, okay, energy wasted increases, then the efficiency, okay, then the efficiency decreases. And that's it. It has to do with the amount of energy wasted. If you waste a lot of energy, then you're not that efficient. If you waste a little bit of energy, then you could be a lot more efficient. Okay? Again, please, if you have any questions, please do not hesitate to ask. What was power? Okay. What was power? It was the work done per unit time. It was the energy over time. Okay. It was the work done over time or the energy over time again. And the unit was watt. Okay. Or W. The unit was watt or W. That was it. Calculate the power, energy over time, or work done over time. Okay. Moving on to the last lesson in Unit 1, pressure. Okay, last lesson in Unit 1, pressure. Pressure was the force per unit area. Pressure equals force over area. Okay, we can use the triangle. Pressure equals force over area. The unit of the pressure was, okay, Newton per centimeter squared or Newton per meter squared. If it's Newton per meter squared, we can write it down as Pascal. Again, if it was Newton per meter squared, we can write it down as Pascal. What if it was Newton per centimeter squared? We'll leave it as it is. Okay, you will leave the Newton per centimeter squared as it is. Do not even think about changing it from Newton per meter squared to Newton per from Newton per centimeter squared to Newton per meter squared. Okay, don't even think about it. Your question?
ولو هو نيوتن بير متر سكوير لازم نحوله ولا مش
لا
هيحصل حاجة
if it's Newton per meter squared, then you can leave it as it is, Newton per meter squared. You will write the unit as Newton per meter squared or as Pascal, as you like. Okay. Again, your course students. Course students, we kind of love the examiners love the course students. Okay. Course students, what do? We just everything is a lot easier. Okay, we don't like to make life harder for you. Okay, someone had a question for power. Power was energy over time. That's it. Power equals energy, okay, over time or work done over time. You can use another triangle. Power equals energy over time, and the time usually has to be in seconds. Okay, we have two types of powers. In a while we'll talk about a different type of energy. Okay, in a while we will talk about the different type of energy, which is the kilowatt hour. But for now, power equals energy over time. That's when we will use the kilowatt. Okay, in a while, just wait a second. Okay. Describe how the pressure varies with the force and area. Okay, again, we usually said when the area, okay, when the area increases, what happens to the pressure? The pressure decreases and vice versa. They were inversely proportional. When the area decreases, the pressure increases. Okay, but with the force, it's directly proportional. If you increase the force, okay, this is directly proportional. If you increase the force, the pressure will increase. If you decrease the force, the pressure will decrease. It's directly proportional. It's that simple. Okay, but the area, this is one of the more popular questions. When the area increases, the pressure decreases. That's why, for example, you have tractors with wide tires. Why do they have wide tires? Because the area increases. As the area increases, the pressure decreases. So usually they won't sink in the soft sand or in the mud. Okay. Again, the pressure due to liquids, liquids, as the depth increases or as the density increases, they are both directly proportional. They are both directly proportional. As the depth increases, the pressure increases. As the density increases, the pressure also increases. That's all you're required to know for the pressure, okay? That's all you're required to know for the pressure due to the liquids. Pressure due to the liquids. You're not required to know this equation, which is written on the right-hand side. This is supplement. You're not required to know it. For your studies, you're required to know that the pressure increases with the depth and with the density, and that's all. Okay, moving on to unit 2, states of matter. States of matter. We know states of matter. Okay, states of matter is one of the easiest sessions we had, I guess. The difference between the solids, liquids, and gases, okay? The changes in states, okay? And you are not required to know gas to solid and solid to gas. You are not required to know sublimation and the other one, okay? You're not required to know, okay? Not required. Again, we're required to know the evaporation, condensation, melting, freezing. You're required to know all of those changes in state. Okay. The structure of solids, liquids, and gases. Yes, we know the structure of the solids, liquids, and gases. We know the arrangement. We know the separation. We know the motion. Okay, we know all of these differences. Okay, you are not required to know sublimation. For in physics, you are not required to know sublimation. Okay. This is the new part added to your syllabus. It is called the absolute zero or the Kelvin scale. What's the Kelvin scale? Okay, Kelvin scale it's a simple temperature. Okay, it's measuring temperature. But instead of using the Celsius, instead of saying, well, today the temperature is 25 degrees Celsius. No, actually, I can actually say today is, let's say, 300 degrees Kelvin. Okay, it's a very simple scale. What do I do? Kelvin is equal to Celsius plus 273. You have to remember this 273. Okay, you need to memorize it. Kelvin equals Celsius plus 273. So for example, if today the temperature was 27 plus 273, so the total temperature in Kelvin would be 300 degrees Kelvin. That's it. So temperature today is, let's say, 300 degrees Kelvin. What if we wanted to find the temperature in Celsius while he was giving me the temperature in Kelvin? How can I find the temperature in Celsius? If he gave me the temperature in Kelvin, what should I do? I'll just flip the equation. So Celsius equals Kelvin minus 273. For example, if the temperature of some liquid, okay, if the temperature of some liquid was, let's say, 400 degrees Kelvin, how to find the temperature in Celsius? 400 minus 273. This will give me a total temperature of 127 degrees Celsius. Okay, you can just flip the equation. Okay, any questions? Okay, good. Pressure due to the gases. Okay, what happens when the pressure, what changes the pressure, or how does the pressure change, or how do gases even exert pressure on the walls? How do we as humans feel the pressure of 100,000 pascals? The atmospheric pressure is 100,000 pascals. You're not required to remember that number, but as humans, we are under constant pressure, which is the atmospheric pressure of how much of 100,000 pascals. How is this pressure exerted on us? It's exerted due to the gas molecules. Again, what happens? The gas molecules move fast and random in all directions, colliding with the surface of the walls, or colliding with us, or colliding with whatever. Do not say that the molecules collide with each other. Never say that the molecules collide with each other. The molecules collide with the surface of the walls, with the surface of the containers, with whatever surface you have, okay? With whatever wall you have, but they do not collide with each other. Again, when they collide with these surfaces, with these walls, what happens? A force is exerted. And the force exerted over a certain area is the pressure. Pressure equals force over area. So when you apply force over a certain area, it will give you some pressure. And the pressure due to one molecule is nothing. But the pressure due to billions of molecules colliding at the same time, this would give a huge amount of pressure. Okay. Know that the random motion of microscopic particles in suspension is evidence for kinetic particle model of matter. What is this? This is the Brownian motion. Again, this is very simply the Brownian motion. What happens in the Brownian motion? The air molecules move fast and random, colliding with the smoke particle or colliding with the pollen grain or whatever you have, okay, causing a random zigzag motion, okay, causing a random zigzag motion. This is the Brownian motion. Okay. Okay, good. Now here's the Kelvin scale. This is the Kelvin scale. Temperature in Kelvin equals Celsius plus 273. Describe describe what happens when you change the temperature, when you change the volume, when you change the pressure. Okay, what happens? PVT, if you remember, pressure, volume, and temperature. Pressure, volume, and temperature. When the pressure was constant, what happened to the volume and temperature? When the volume was constant, what happened to the pressure and volume? When the temperature was constant, what happened to the pressure and volume? Okay. I can write it down very quickly right now. If I had a constant, okay, if I had a constant pressure, what happened as temperature increased, the volume increased, okay, because this was constant pressure. So for example, you have a balloon. If you heat up the balloon, what will happen? The volume will increase. This is due to constant pressure, okay, and vice versa. If I decrease, okay, if I decrease the temperature, the volume will decrease, okay. Okay, constant pressure. What about constant volume? If I had constant volume, then the PVT, the pressure and the temperature will change. When the temperature, okay, as the temperature increases, what happens to the pressure? As the temperature increases, what happens to the pressure? Pressure increases as well. Okay, the pressure increases as well. Okay, due to the molecules moving faster and hitting the walls harder. Shabab, you have to memorize. Okay, you have to remember that as the temperature increases, the kinetic energy of the molecules increases. You have to remember this. When the temperature increases, the kinetic energy of the molecules increases. Okay, and finally, when we talked about the constant temperature, temperature as, okay, so in constant temperature, the volume and the pressure will change together. As the volume, okay, as the volume decreases, what happened to the pressure? The pressure increases. Okay, if you have a balloon and you decreased its volume, if you compressed this balloon, what will happen? The pressure will increase definitely. Yes. Okay. Okay. Good. Constant pressure, constant volume, and constant temperature. This was PVT. And then we talked about the thermal expansion. Okay, if you have any questions, please don't hesitate to ask. Okay. Thermal expansion. Again, thermal expansion, solids, liquids, and gases, whatever state you have, شباب, if you increase the temperature, the volume will increase. But the expansion of the gases is the greatest because the distance between the molecules is already great, and the expansion of the solids is the least because the distances are already very tightly packed because there are very strong forces between the molecules. Okay. Again, describe some everyday applications and consequences of thermal expansion. Applications, one of the very famous applications is a thermometer. Okay, and one of the very famous consequences is the buckling Okay, buckling of train tracks. Okay, these are some of the applications and consequences of thermal expansion. Specific heat capacity. Okay, you're not required to know specific heat capacity per se. Okay, but you're required to know as the temperature increases, okay, the internal energy also increases, which is the kinetic energy. Okay, someone had a question. Pressure directly proportional. Pressure and temperature are directly proportional. Yes, they are directly proportional. As you increase the temperature, the pressure increases. Yes, in constant volume. Temperature and volume directly proportional. Temperature and volume are directly proportional. Yes, okay. Pressure and volume are inversely proportional. Yes, pressure and volume are inversely proportional. If you had, let's say, a piston, for example, if I have a piston, this is a cylinder and a piston inside, okay, and I had some air molecules inside this piston, okay, I have 5 air molecules, let's say. If I push it inside, okay, if I push it to the left, what will happen? The volume will decrease. صح? The volume now decreases. Okay, the volume now decreases. So as the volume decreases, the pressure, what will happen to the pressure? The pressure will increase. Why does the pressure increase? Why does the pressure increase? Because the area of the walls decreases. The area of the wall decreases. And we said pressure equals force over area. Pressure equals force over when the area decreases, what happens to the pressure? The pressure increases. Okay. Okay, you have question?
مستر هو هنا الفورس بتنكريز ولا لأ؟
لا, الforce remains the same. In this question, the force remains the same. Why does the force remain the same? Because the molecules have the same kinetic energy. You do not change the temperature. Okay, you do not change the temperature. Okay. Okay. Uh, Inversely. Okay. Uh, rules don't make sense. There are no equations. You're not required to know any equations for this one. Okay. You're just required to know that as it increases, as the temperature increases, the volume increases. As the temperature increases, the pressure increases. But as the volume decreases, the pressure increases. This is inversely proportional due to one equation. Okay. You're only required to know one equation. Pressure equals force over area. And that's it. Okay. Don't go into too much details. Don't make it hard for yourself. It's very easy. Believe me, it's much easier than you think. Okay. Okay, moving on. Again, if you please, I do encourage you to ask questions. So I like your question. If you, again, if anyone has any other questions, please don't hesitate to ask. Melting, boiling, and evaporation. We know the processes. We know them. Describe melting and boiling in terms of energy input without the change of temperature. We know that as we melt or as we boil any substances, the temperature does not change, okay, without the change of temperature. For example, the melting is at 0 degrees Celsius, the boiling is at 100 degrees Celsius. So the water will keep on boiling. The water will keep on boiling at 100 degrees Celsius. The energy is applied. What happens to this energy? Okay. Does it increase the temperature? No, it doesn't increase the temperature. What happens? It breaks down the bonds between the water molecules to change them into water vapor, into steam. Okay. Yes, you are required to know the temperatures, 0 degrees and 100 degrees Celsius, condensation and solidifications in terms of particles, okay, that the particles get closer together in condensation and in solidification. Describe an evaporation. We know evaporation. And we know what it causes. Again, what happens in evaporation? Most energetic molecules escape from the surface, leaving behind the least energetic molecules, causing the average temperature of the liquid to decrease or causing a cooling effect. Okay. How does it cause the average temperature to decrease? Because the average kinetic energy of the molecules decreases. Because the most energetic molecules have now escaped. صح? Most energetic molecules have now escaped. That's it. Okay, this is evaporation. Again, the difference between the evaporation and boiling was very simple, that the evaporation only happened on the surface, but the boiling happened throughout the whole surface. Evaporation happened at any temperature, but boiling happened at only specific temperatures. Okay, I know you're not required to know it because this is a supplement. You're not really required to know it, but it's يعني, it wouldn't harm to know it. Okay. Okay. Conduction. Volume constant, does increasing pressure increase temperature? Eh? No. When the volume is constant, not the increasing pressure increases the temperature. It's the other way around. When the volume is constant, when you increase the temperature, the pressure increases. Okay. Um. Okay. Conduction. Energy transfers. We have three types of energy transfers: conduction, convection, and radiation. Conduction. What was conduction? It was mainly in solids. We had to differentiate between good conductors and bad conductors. We know that the good conductors are the metals, and bad conductors are usually insulators. Most of them are non-metals. Why are metals good conductors? Because they have free moving electrons. Because they have free moving electrons. Good conductors. Why are bad conductors bad conductors? Why don't they conduct energy or heat quite efficiently? Because they don't have free moving electrons. Okay, it's as simple as that. Okay, moving on to convection. Conduction. Again, conduction, it does occur in metals and non-metals. It happens in whatever solid you have. Actually, conduction does occur in liquids and gases, but we usually say that in liquids and gases it's um, not that much, and that's why we don't actually consider it to happen in liquids and gases. But it does occur in liquids and gas. Mainly conduction is in mainly conduction happens in solids. Okay. Convection, which was easier, harder, I don't know, maybe. Know that the convection is an important method of energy transfers in liquids and gases. Yes, we know. Okay, what happens in convection? Okay, what happens in convection as the temperature increases? As the temperature increases, the kinetic energy increases. So when the kinetic energy increases, what happens to the volume? The volume also increases. When the volume increases, what happens to the density? Density decreases. When the density decreases, the hot liquid or the hot gas moves up. Okay, the hot liquid or the hot gas moves in. Okay, moves up, and the cold liquid or the cold gas moves down. Okay, cold liquid or cold gas moves down. Okay, that's it. Convection. Radiation. Okay, radiation. What happens in radiation, يا شباب? We know that the infrared radiation, not any type of radiation. Okay, infrared radiation is the one responsible for the heat, and that's why I have to say energy is transmitted using infrared radiation, not using radiation, not using, for example, ultraviolet radiation or light radiation or whatever other type of radiation. No, the heat is transferred using infrared radiation. It is the only type of heat transfer that does not require a medium. Why? Because it is an electromagnetic wave. Electromagnetic waves can move in vacuum. The sun, for example, okay, the sun heats up the earth. The sun heats up the earth using what? Using the infrared radiation. For example, it lights up the earth. Okay, we receive the light using the light radiation, and that's why we have to differentiate. We have to say that the heat, okay, is the infrared radiation. Okay, describe the effect of the surface if it's black or white. Okay, and if it's dull or shiny, if it's black or white, or if it's dull or shiny. Definitely, we know that the black or the dull black, we know that the dull black is the best emitter and best absorber. best emitter and best absorber. And we know that the shiny white is the worst emitter. Okay, yeah, worst emitter and worst absorber. Best, worst, worst. Again, when do I say emitter or absorber? Emitter is if the object is hotter than its environment. Absorber if the object is colder than its environment. Emitter if it's hotter, colder if it's or absorber is when it's colder. Infrared radiation, yes, it is an electromagnetic radiation. Yes, it is an electromagnetic radiation. That's why it can travel in the vacuum. That's why it moves at the speed of light, which is 3 times 10 to the power of 8 meters per second. Okay, good. Okay. Consequences of thermal energy transfer. Okay. Heating up objects such as kitchen pans, heating up the room by convection. Okay, we know these consequences. Again, you're not required to know the supplement. Okay, you're not required to know anything on the right-hand side. That's it. Okay, so now we're done with unit 2. We're done with unit 2. Unit 3, waves. Okay. Any questions before I move on to unit 3? Any questions before I move on to the waves unit? Hello. Okay. Okay. Again, if you have any questions, please don't hesitate to ask. In waves, I'll still لسه. Okay. Waves. لازم أعرف أرسم wave fronts. You have to know how to draw a wave fronts. Okay, we'll see now. Okay, don't don't worry. What is a wave? What is a wave? Wave is the transfer of energy. It's the propagation of energy without without transferring matter. Okay, it's the transfer of energy without transferring any matter. Describe what is meant by the wave motion, okay? Such as let's say, the longitudinal waves, the transverse wave. Again, when we say the difference between the longitudinal and the transverse, longitudinal moves left and right parallel to the energy motion. Transverse moves up and down perpendicular to the energy motion. We know, okay, some of the features. We know what is a wavefront, a wavelength, frequency, crests, troughs, amplitude, and speed. And we can calculate the speed. Speed equals wavelength times the frequency. What is a wavefront? What is a wavefront? If I had a wave moving this way, a wavefront is this perpendicular line. Okay. These perpendicular lines are called wave fronts. Each of them is a wave front. It represents, what does a wave front do? Okay, what does a wave front do? For example, it represents the crest of a wave or the trough of a wave. Doesn't matter. Okay, it represents what? The crest of the wave. So this is called a wave front. The distance between one wave front and the other is the wavelength. The distance is the wavelength. These distances are the wavelengths. Okay. Again, what is the direction? This is the direction of the wave. Okay. This is the direction of the wave. Direction of the wave, in this case, it's moving from the left to the right. Okay, it's moving from the left to the right. These perpendicular lines that I've drawn are called the wave fronts. Each of these wave fronts represents a crest. Each of these wave fronts represents a crest. What is a crest? This is a wave. Okay, this is another wave. This is a different wave. So each of these crests is a wave front. And the distance between the crest and the crest is the wavelength. The distance between this crest and this crest is the wavelength. The same applies as the distance between these wave fronts is the distance between these wave fronts is the wavelength. Okay. بس that's it. Okay, that's it. How do we find, for example, the amplitude? Okay, the amplitude, we can find the amplitude in a transverse wave. Okay, the amplitude would be the distance between the crest and this line, which is moving. Okay, or the distance between the trough and this line. This would be the amplitude. This would be the amplitude. Wavelength, and then how do I find the speed? The speed is the wavelength times the frequency. I can define the frequency. We can define the frequency. What is the frequency? It is the number of number of what? Number of waves per unit time or per second. Okay, number of waves passing per unit time. Okay, or per second. Usually it's per second. The unit of the frequency is what? Is hertz. So you can calculate the frequency. We can find the frequency quite easily. Okay, frequency equals waves over time. Okay. Okay. Again, what is a transverse wave? Moves up and down, perpendicular, right angles. Okay, right up and down, perpendicular to the energy motion. All of the electromagnetic waves are transverse. All of the water waves are transverse. Seismic waves. This is a new addition to the syllabus. Seismic waves are transverse waves. Okay, how could I remember it? Okay, how to memorize it? Transverse. Okay, transverse. Okay, S is seismic. You can remember it. If you have an S wave, okay, if you have an S wave, this is a transverse wave. We have another type of waves. It's called a P wave. We'll state it now. Okay, a P wave. This is a P wave. What's a P wave? It would be a longitudinal wave. But if you have an S wave, S is transverse. S and S. S is a transverse wave. Okay. That's if he asks. For example, he could ask you, what type of wave is a seismic S wave? It would be a transverse wave. If it was a P wave, it would have been a longitudinal wave. Okay? No, for a longitudinal wave, it moves parallel, left and right. Okay, parallel, left and right, such as the sound waves, one of the most famous longitudinal waves. Okay. Okay, hello. How can waves undergo reflection, refraction, and diffraction? Reflection, refraction, and diffraction. We know that reflection, the angle of incidence would be equal to the angle of reflection. Refraction, due to the change of speed, okay, this is quite important to remember that, okay, you have to remember this actually, okay. What happens during refraction? The speed changes. Again, you have to remember this. What happens during a refraction? The speed changes, and that's why it refracts. That's why, okay, the angle changes. That's why the wavelength changes. Refraction happens why? It happens due to a change of speed. Okay, diffraction, when it passes through a narrow gap. When it passes through a narrow gap. When it passes through a narrow gap, what happens? It diffracts. It starts to spread. Okay, spreads. Okay, it starts to spread this way. Wave speed is higher in water or air. It depends. Okay, the speed is, if it's higher in air or water, it depends. It depends on the type of wave. If it was a light wave, and we're going to discuss this now. Okay, if it was a light wave, it would move faster in air. If it was a sound wave, okay, if it was a sound wave, it would move faster in solids. Okay, the fastest sound waves are found in solids. The fastest light waves are found in vacuum or in the air. Okay, ماشي. Describe the ripple tank to show. Okay, this is one of the lesser يعني known questions. If I have a ripple tank, if I have some water, I want to find the reflection, the refraction. Okay, we know the refraction. Okay? You know the refraction of the liquids. You know the refraction of the waves in liquids. What happens? For example, if you had a deep end and a shallow end, okay? If you have a deep end and a shallow end, for example, you would have a large wavelength, and then moving on to the shallow end, what will happen? The wavelength will decrease. This is the deep, and this is the shallow. Are we required to know if the speed increases or decreases during refraction? Um, kind of, yes. Yes, okay. But again, you have to know the type of the wave. You have to know if it is a light wave or a sound wave. If it's a light wave, it could move, okay, it could move the fastest in the air and the slowest in the glass, for example. Okay, and vice versa with the sound waves. It's the fastest in the solids, but the slowest in the air. Okay, again, we had the diffraction due to a gap, a diffraction due to an edge. What's the diffraction due to an edge? Okay, I can draw it over here, for example. If I had the diffraction due to an edge, okay, so I had the wavefronts moving like this. Okay, these are the wavefronts moving. This is the direction of the motion. What happens after they pass through the edge? They start to diffract this way. They start to diffract this way. Okay. This is the diffraction due to an edge. Okay. And then reflection on a plane surface when it reflects angle of incidence equals angle of reflection. What is a ripple tank? A ripple tank is a water tank. Okay. It's a water tank. Okay. If I had some water in a tank, they would create some ripples. What is a ripple? Okay. Ripples are the waves in the water. Water waves. These are what we call ripples. Okay. And that's it. Reflection. Reflection of light. Define and use the term normal, angle of incidence, and angle of reflection. I guess we all know them. Normal line, angle of incidence, angle of reflection, formation of an optical image by a plane mirror. Yes, plane mirror. Characteristics of a plane mirror. We have some characteristics. Same size, same distance, and that it is a virtual image. It's what? It's a virtual image. And we discussed what a virtual image is. Okay, we did discuss what a virtual image was. What's a virtual image? It's an image that cannot be reproduced again. For example, you cannot produce this image on a screen. You cannot save this image. You cannot print this image, for example. You cannot send it to some of your friends, for example. Okay, what's a virtual image? It's an image that appears once you are looking through a. It isn't permanent. No, it is. It's not permanent. Okay, it's not permanent. When you look through the mirror, you can see your image. Once you go away, what happens to this image? It disappears, and that's what I mean by a virtual image. Okay, it's a non-permanent image. it's a a virtual image. You cannot print this image. Okay. And then we all know that the angle of incidence has to be equal to the angle of reflection. Okay, I equals R. Any problems? Any questions? Okay, moving on to the refraction of the light. Again, using the normal angle of incidence, angle of refraction, we know them. How to show the refraction of light while it's passing through a block, for example, that it bends towards the normal. Okay, it bends towards the normal. Describe the passage of light through a transparent material. Okay, okay, as it bends towards the normal. What is meant by the critical angle? طب واحدة. Okay, as it moves from air to glass, or as it moves from air to liquid, what happens to the light? It bends, it gets closer. Okay, let's say that this is the glass and this is the air. As the light moves from the air, okay, you have to draw the arrow. Okay, as it moves from the air to the glass, this is the normal. What happens, and this is the angle of incidence. This is the what happens, it gets closer to the normal. Bends, it gets closer. This would be the angle of refraction, I and R. It gets closer to the normal. As it gets closer to normal, the angle of refraction decreases, the wavelength decreases, the speed also decreases, huh, as it moves from the air to the glass. What happens if it moves from the glass to the air? What happens when it moves from the glass to the air? The speed increases, the angle increases. It moves from the from the glass moving to the air. What happens? The speed, the angle increases. Angle. That's why it's very important. Okay, it's very crucial to put the arrows on your lines. Okay, on your waves. It's crucial to draw the arrows. This is the angle of incidence, and this is the angle of refraction. Okay. What's a critical angle? Okay, frequency is the same. Yes, frequency does not change. Yes, bro. Okay, frequency does not change. What is a critical angle? A critical angle is an angle of incidence. It's an angle of incidence from the glass or from the more dense medium. It doesn't have to be glass, it could be water. Okay, it's an angle of incidence from the more dense medium. At which, what happens? What happens? The angle of refraction becomes 90, or the refracted ray moves along the surface. What's a critical angle? For example, this was my angle of incidence, but the angle of incidence has now increased. Okay, angle of incidence has now increased. Let's say it becomes around 40 or 42 degrees. Okay, let's say this is my angle of incidence and this is the normal. Okay, this angle of incidence has now increased to become, let's say it's 42 degrees. You are not required to memorize this number. It changes. It could be 42, it could be 45, it could be 43, it could be 40. Okay, you are not required to memorize the number. Okay, you're just required to know that it is an angle of incidence from the more dense medium. This is the more dense medium. This is the glass. At which, what happens? What happens, شباب, when I'm moving from the more dense to the less dense? The angle of incidence increases. Sorry, the angle of refraction increases, but it increases up to a certain point. What is this certain point? It is the critical angle. It is the critical angle. What happens in this critical angle? What happens to the refracted ray? It moves along the surface. The refracted ray moves along the surface. Where's the angle of refraction? Okay, this is the angle of refraction. It's 90 degrees. This is the angle of refraction. Again, I know this is a tricky part. Okay, this is the angle of refraction. It's 90 degrees. Again, what is the critical angle? What is the critical angle? It's an angle of incidence. Angle of incidence from the more dense medium. From the more dense medium. It has to be moving from the more dense medium. Why? Because the angle will increase. Because the angle of refraction has to increase. If it was moving from the air to the glass, for example, if the ray was moving from the air to the glass at an angle of incidence of 42, what would happen? The angle would decrease. It would be less. It would be 25 degrees, for example. Okay, so it will never reach 90 degrees if it was moving from the air to the glass. It has to be moving. It must be moving from the glass to the air. It must be moving from the water to the air, from the more dense medium to the less dense medium. Okay, so it's an angle of incidence at which the refracted ray moves along the surface. Oh, where's the refracted ray? It's this blue ray. Refracted ray. This is refracted ray. What happens to the refracted ray? It moves along the surface. It does not move, for example, with an angle of 80 degrees or 70 or whatever other angle. No, it only moves along the surface with an angle of 90 degrees. That's it. That's the critical angle. طب يبقى so the critical angle is 90 degrees? No, the critical angle in this case is 42. This is the critical angle. Okay, this is the critical angle. It's the angle of incidence. Okay, it's not the refracted angle. Okay, it causes the refracted angle to move along the surface, but it's not the refracted angle. It's an angle of incidence. Okay, it's the initial angle of incidence. Okay, critical angle. Why is it critical? Okay, why is it critical? Because if the angle of incidence now increases above 42, if the angle of incidence now increases above 42, what will happen? Total internal reflection. Again, if the angle of incidence increases above the critical angle, it doesn't have to be 42. It doesn't have to be 42. It could be 43, whatever. Okay, if it increases above this critical angle, what will happen? Total internal reflection. So, for example, okay, if I had my boundary, this was the glass and this was the air, and the angle of incidence was much greater. Okay, let's say that the angle of incidence here is 50 degrees. What will happen? Total internal reflection. No light, no rays, nothing will exit. Nothing will move outside. Okay, nothing will move outside. All of the rays will be reflected back inside. I know it's tempting. Okay, I know it's tempting to write down reflection. But if you, for any reason, write down reflection, it would be wrong. It's not reflection. Okay, it is not called reflection. It's called what? Total. You have to say total internal reflection. If for any reason you write down reflection and that's it, you will lose a mark. You will definitely lose a mark. So what it's called? It's called total internal reflection. Okay. ماشي حلو. Any questions? Any questions? Moving on to lenses. Moving on to lenses. We had two types of lenses. The more common type, the one which we have all of our questions, okay? All of our questions are concerning the converging lens, okay? Convex lens. All of the questions. A new type of lens has been added to the syllabus. It's called a diverging lens, okay? This is a new type of lens. Do we have any questions regarding this diverging lens? No. Are we required to know a lot about it? No, we're not required to know a lot about it, but we can just know very simply what is a diverging lens. Very simply, okay? We'll discuss it right now. What a diverging lens? Okay, we know a diverging lens, how a diverging lens acts. Okay, how do the rays act when they pass through a converging lens? This is a converging lens. Okay. Okay, this is a converging lens. If this is the focal point, if you had any parallel, rays, what do? They pass through the focal point. If you had any parallel rays, what do? They pass through the focal point. If you had any rays passing right through the center, okay, what happens? Nothing. They will continue in a straight line. If you have any rays passing through the center, okay, they will move on in a straight line. That's it. Parallel rays move and bend towards the focal point. Rays passing through the center, they don't get refracted. Okay, we know the difference between the focal length, the principal axis, and the principal focus. Okay, what is the focal length? What is the focal length? Focal length is the distance between the center and the F. This is the focal. This is the focal length. What's the principal axis? Because you usually tend to forget what's the principal axis. The principal axis is this dashed horizontal line. This is the principal axis. What is the principal focus? It's the F. It's the focal point, okay? This F is the principal, okay? It's the principal focus. You can name it focal length, or you can name it the principal focus. It's okay. Either or. Principal focus or focal point. But the focal length is the distance between this principal focus or the distance between this focal point and the center of the lens. Okay? Again, you can recall some of the rays which we drew in a converging lens. The parallel ray has to bend and move through the focal point. The ray moving through the center will continue in a straight line. It will not bend, it will not refract. And then we had some of the characteristics. It could be enlarged, same size, or diminished, depending on the image. Okay, depending on the image. If the image was much larger than the object, this would be enlarged. Okay, it would be larger. If the image was smaller, for example, if you had a very small image, it would be diminished. If it was the same size, خلاص, I will name it same size. Upright or inverted? Is it upright or is it inverted? If it's looking downwards and the object is looking upwards, then it would be called an inverted image. And real versus virtual. What is real versus virtual? And this is actually, you're required to know this part. Real versus virtual. Real versus virtual. What is a real image? What is a real image? And what is a virtual image? Okay, we have 2 points. Real versus virtual. Real images, okay? Real images are those inverted images. Real images are those, are those inverted images. If you have an image which is inverted, it's on the other side, it would be a real image. When is it called a virtual image? When is it called a virtual image? For example, if you had, let's draw a simple ray. Okay, let's draw a simple, okay, lens. Okay, and if this is the object, and the image, for example, appears on the same side. If this is the image, if it appears on the same side and it appears to be upright, this is upright. It's enlarged. Okay, it is enlarged. It will be a virtual image. Upright, enlarged, and virtual. When do I have a virtual image? When we only have one case. We only have one case when we use a lens to find a virtual image or to produce a virtual image. If you recall, we just talked about the virtual images, okay? We just talked about the virtual images when we said virtual images are images or let's say the plane mirror images. All of the plane mirror images are called virtual images. Yes. But when we use a lens to produce a virtual image, this is in only one rare case when we use something called the magnifying glass. This is when we use what? A magnifying glass. You didn't even find any questions regarding the magnifying glass in your classified questions, okay? But again, what is a magnifying glass? It's a glass, it's a lens which produces what? It produces a virtual image. Why? Why is it the virtual image? Because while using this magnifying glass, you can see the image. Once you remove the magnifying glass, what happens to the image? It disappears. It disappears. You cannot save this image. You cannot produce this image on a screen. You cannot print this image that you can see through this magnifying glass. But again, whenever I have a magnifying glass, it produces an image. This image has to have these 3 properties, which are the image is always upright, it is always enlarged. That's why it's magnified. Literally, that's why we called it a magnifying glass, because the image is enlarged. and it is a virtual image because I cannot save this image. I cannot produce this image on a screen. Okay. This is a very rare case of a virtual image being used or being produced by a lens. Okay. Again, these are all uses of the converging lenses. These are all uses of the converging lenses. Again, okay, again, whenever I have a converging lens, any light that's passing in a parallel manner, it will be refracted through the focal point. If it's going through the center, okay, if it's going through the center, what will happen? It will continue in a straight line and then it will not be refracted. The intersection of these two lines, for example, if you continue these two lines, okay, the intersection of these two lines will produce a image on the opposite side, okay? What is a diverging lens? Okay, what is a diverging lens? One of the new points. You're not required to know much about the diverging lens, to be very honest. You are not required to know much about a diverging lens. But what is diverging? Diverging means that the rays move away. Okay, diverging means that the rays move away. Converging means that the rays move together or closer. Let me draw a diverging lens here, for example. Okay, how does a diverging lens look like? This is a simple drawing of a diverging lens. Okay, it is opposite to the converging lens. What do I mean? Okay, if I have a ray moving parallel, okay, it's moving parallel this way, what will happen? It will move away. That's it. If it's moving parallel, what will happen, Shbab? It moves away from the lens. That's it. That's all you're required to know. If I had a parallel ray, what happens? It moves away from the lens. It diverges, literally. That's what I mean by diverging lens. Okay. Diverging means that it moves away. They don't move closer. No, they move further away. That's it. That's what I mean by a diverging lens. And that's it. Okay. You're not required to know much about the diverging lens. Of course, you have the principal axis in the middle. This is called the principal axis. Okay. This is the principal axis. Of course, it's parallel. Okay. This is the principal axis. That's it. You're not required to know much about the diverging lens. All you are required to know is that the rays move away. Okay. A line in this is called the center. This is the center. Okay. And this is the principal axis. This is the principal axis. Again, it's almost the same, but the difference is what the lines in or the rays in the diverging lens move away. The rays in the converging lens move towards, for example, the focus. You have the focal point. Okay. You draw a red. The red is the diverging lens. This is the diverging lens. Okay. This is the lens. Okay. Instead of drawing it this way, this is a converging lens. This is the diverging lens. That's it. Okay. That's the simple difference between a converging lens and a diverging lens. Okay. Converging and diverging. حلو. Okay. I hope. يلا. Let's finish up unit 3. Dispersion of light. Well, we definitely know dispersion of light. What happens to the light as it passes through a prism? What happens to the light as it passes through a glass prism? It gets dispersed. It gets split into the 7 colors. We know the 7 colors. Roy Gibev. Okay. Roy Gibev. Roy Gibev. We have to know them in this order. We also have to know that the red is the least frequency and the highest wavelength, or the longest wavelength and the least frequency. The violet is the complete opposite. Okay, it has the shortest wavelength and the highest frequency. You need to know them in this order. Okay. And then moving on to the electromagnetic spectrum. We can recall the electromagnetic spectrum. If you recall, Rami looks great. RMI. Rami. looks great. RMILUXG, radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. They they are all electromagnetic waves. Electromagnetic waves means that they move or can travel in the vacuum. Okay, they can all travel in the vacuum. Dispersion, you still have a problem with dispersion? Huh. Dispersion. Dispersion هو the splitting of the light. The light splits into 7 colors. We have 7 colors. Roy Gibev. Red, orange, yellow, green, blue, indigo, and violet. This is what we call dispersion. They have to be in this same order. They have to be in this same order. The red has the longest wavelength and the shortest or the least frequency. The violet is the complete opposite with the shortest wavelength and the highest frequency. Okay, you just have to know them in this order. Okay. Again, electromagnetic spectrum, Rami looks great. And we need to know some of their uses. Okay. We need to know some of their uses. Radio waves, we know that radio waves are used in communications without any satellites, such as radio, television, okay? Something called RFID, radio frequency identification, okay? Radio frequency identification, RFID. This is radio waves. Microwaves are used in, we know that microwaves are used in cell phones and microwave ovens, okay? Satellite television, anything that has to do with satellites uses microwaves. Okay. Infrared electric grills, anything that has to do with heating. صح. Anything that has to do with heating. Remote controllers. Okay. Intruder alarms, thermal imaging, and last but not least, something called the optical fibers. Okay. You will not, okay, as course students, most likely you will not be required to know this optical fiber. Okay, you will not be asked about what happens inside the optical fiber. As course students, you are not required to know what happens inside an optical fiber. You are just required to know what is the type of electromagnetic wave that is used inside an optical fiber. Okay, it is an infrared wave, or sometimes it's called a light wave. Okay. But again, as course students, you are not required to know what happens inside the optical fiber. Okay? Okay. Again, visible light. We know that visible light for vision, photography, illumination, whatever. Then ultraviolet security marking. What is security marking? It's such as the detecting. Okay, like it's the same as the detecting fake banknotes. Okay, sterilizing water. Okay, it has some uses. Again, we said tanning beds, okay, which is correct. We have a lot of uses for the ultraviolet radiation, security marking, detecting fake banknotes, sterilizing water. Okay, X-rays. We know the uses of the X-rays, medical scanning, okay, and security scanners. Medical scanning for broken bones, for example, and security scanners. Well, you know the security scanners. Again, moving on to the gamma rays, sterilizing food, medical equipment, detection of cancer, and treating cancer. It was a very, very theoretical part, if you can recall. It was too much theory in this part. Okay. Moving on to the harmful effects of these radiations. Microwaves and infrared, they both have to do with burning, okay, or skin burns or heating. Okay, they both have to do with the heating. Okay, both of them have to do with the heating. On the other side of the spectrum, it has to do with the damaging the cells, it has to do with skin cancer, okay, has to do with mutation, okay, to the cells or whatever. We have Rami, looks great. This side of the spectrum has to do with the heating. Okay, it has to do with the skin burns. This side of the spectrum has to do with the cancer, mutation, okay, skin damage, these things. Okay. Again, No. Okay, we need to know this part. Some satellite phones use low orbital satellites. Again, we know that the satellite phones that they use the microwaves, okay, and that they use something called the geostationary satellites. Will we really be asked about these points? Probably not. Okay, probably not. But it's quite useful to just read it again. Know that communication with artificial satellites is mainly by microwaves. Okay, we know this part. We know that any satellite, uses a microwave. Some satellite phones use low orbit artificial satellites. Some satellite phones and direct broadcast satellite television use geostationary satellites. So we have two types of satellites. It's either a low orbit artificial satellite, it's either a low orbit satellite or a geostationary satellite. Will I really ask you, or will you really have any questions regarding them? Probably not. Okay, probably not. But it's quite useful to just read them again. Low orbit satellites or geostationary satellites. Okay. Um, you had a problem, Hannah? Okay. Someone had a problem, huh? Rami looks great. Okay. Either microwaves and infrared. Okay. And ultraviolet and X-rays. Okay. Have a question?
هي ايه اليوزز بتاعت الراديو ويفز ولا ملهاش؟
Oh, radio waves using in the radio fly and the television transmission without satellites. Television transmission without satellites. Astronomy, radio frequency identification, RFID. Okay. على فكرة there's one more use for the radio waves. The Bluetooth communication. Bluetooth communication. It uses the radio waves. Okay. Yes, you have them in your notes. Okay. Bluetooth communication uses the radio waves. Okay. Okay. Yeah. Sound waves. Last lesson in unit 3. Okay. Does everything around us deliver waves? Does everything around us deliver waves? What do you mean by that question? Okay. If you can, please tell me more. Okay. Let's talk about sound waves. What is a sound wave? Sound wave is a wave that is produced due to a vibrating source, any vibrating object, okay, could produce a sound wave, okay, could produce a sound wave. Describe the longitudinal nature of sound waves. We know that the sound waves are longitudinal. They move left and right parallel to the energy motion. We know that the audible frequencies are from 20 hertz to 20,000 hertz. We know that it is a mechanical wave. Okay. It's a mechanical wave. It requires a medium. Sound waves cannot travel in a vacuum. If you have a vacuum, you have no matter. Sound waves cannot travel in a vacuum. And last but not least, the sound waves have a speed usually of 330 to 350 meters per second in air. In air. When it moves in liquid or in solids, what happens to the speed? The speed increases. Okay. What happens to the speed? The speed increases. Okay. Okay. ماشي. Again, sound. How can I measure the speed of sound in air? We had a very simple experiment. What was this experiment? When we had two students, one of them had a sound or a smoke gun, and the other had a stopwatch. They had to measure long distance between them. They had to measure a distance of at least, let's say, 600 meters, for example. Okay, using a measuring tape, very long distance. And then when student A fires the smoke gun, student B, whenever he sees the smoke, he will start the stopwatch. And then when he hears the sound, he stops the stopwatch. And then he has the time difference and he has the distance. And then he can calculate speed equals distance over time. Okay. Changes in amplitude and frequencies. Yes, when the amplitude changes, the loudness changes. When the frequency changes, the pitch changes. They are both directly proportional. As I increase the amplitude, the loudness increases. Okay, it becomes a very loud sound. As the pitch increases, sorry, as the frequency increases, what happens to the pitch? The pitch also increases. Okay, the pitch increases, but they are both directly proportional and they do not affect each other. For example, if the loudness increases, does that mean that the pitch also has to increase? No, not at all. Okay, you can increase the pitch and, for example, at the same time decrease the frequency, or increase the pitch and the frequency. I'm sorry, you can increase the pitch and at the same time the loudness will remain the same, or you can decrease the loudness or whatever. The frequency has to do with the pitch. When you increase the frequency, the pitch increases. You increase the frequency, the pitch increases. When you increase the amplitude, the loudness increases, and vice versa. And that's it. Okay. Reflection of the sound. What is the reflection of the sound? It's called an echo. What's the reflection of the sound? It's called an echo. How can we calculate the speed of an echo? Huh? When we calculate the speed of an echo, we used two distance over time. Why was it two distance? Because the sound moved two distance. It went all the way to the wall and back. Okay, it went all the way to the cliff and back. So two distance over time. This was the echo. And last but not least, any sound with a frequency above, a frequency higher than 20,000 hertz is called ultrasound. Any sound with a frequency, you have to state that it has a frequency above 20,000 hertz. Whenever the frequency is much greater than 20,000 hertz, okay, we name it an ultrasound because we as humans cannot hear it. Other animals could hear this frequencies, yes, but as humans, we cannot hear frequencies above 20,000 hertz. Okay. Okay. That's it for today. Okay.